Now we're going to briefly take a look at the structure of substituted alkanes, and we're going to start talking about alkyl halides. Now, if you look at the carbon attached to any of the substituted alkanes, you see that the carbon is nearly tetrahedral. Obviously, unless it's an sp2 hybridized carbon. So we're assuming that the carbon is sp3 hybridized for alkyl halides because we're talking about an alkyl group. If we were talking about a vinyl group, then it would be different. But here we're just talking about simple alkyl groups, right? And if you think about the bond between the carbon and the halogen, it involves the overlap of a singly occupied carbon sp3 orbital with a singly occupied halogen orbital. You can think of that halogen as being sp3 substituted. You can think of it as not being hybridized whatsoever. It doesn't really matter. The key is that that halogens have one orbital that only has a single electron in it, and it is that orbital that is going to overlap with one of the carbon sp3 orbitals, right? So those are the atomic orbitals that are going to mix to form a new molecular orbital that is a sigma bond, and then a new sigma star antibonding orbital. And so in terms of the shape of that that sigma orbital, it looks something like this, because if the halogen is let's say that singly occupied p orbital and I mix with an sp3, then I get a new molecular orbital that has high electron density in between the two, and of course there's some electron density on opposite sides of both of the elements, both of the atoms, right? So it looks something like this. Now, when you think about the strength of that bond, if we're assuming the overlap is from a p orbital, as you move down the periodic table, the n value, the principal quantum number, gets larger. And as we know, when the principal quantum numbers are not the same, then overlap isn't the same as well. It weakens as the difference in n gets larger. So we can look at that relative to bond strength. And if we start with the carbon-fluorine bond, carbon and fluorine both have n equals 2, so the overlap is, we would predict to be very strong. And the bond strength of that carbon-fluorine bond is 115 kilocalories per mole. Now when we move to carbon-chlorine, now chlorine is in an n equals 3 shell, and we would expect that bond strength to weaken, and as a matter of fact it does. And you can see this trend kind of follow. Carbon-bromine bond is weaker at 72 kilocalories per mole, and when you get to carbon-iodine where n equals 5, you see a huge reduction in the bond strength. So it's very easy to break a carbon-iodine bond. And much harder to break a carbon-fluorine bond. And we're going to see the importance of this role later on when we look at the reactivity of alkyl halides. Now, moving on to alcohols, we can think of alcohols as organic derivatives of water. And I've used this term before, but certainly, you can think about the structure of water and you can relate it to the structure of alcohols. So we know that the structure of water looks something like this. We know the bond angle of the hydrogen-oxygen-hydrogen bond is 104.5. Sometimes we simply round to 105 degrees. We also know that the bond length between the oxygen and hydrogen is about 0.96 angstroms. If I compare this to methanol, where instead of essentially substituting one hydrogen for an alkyl group, a methyl group, what does that methyl group do to the structure? Well, it certainly increases that bond angle a little bit to 108.9 because the methyl group is taking up more space. Notice the oxygen-hydrogen bond length is virtually the same, but a carbon-oxygen bond length is considerably longer at 1.43 angstroms. Now, how does this compare to a carbon-carbon bond? Well, if we look at the structure of ethane, we can see that the carbon-carbon bond length is 1.54 angstroms. So a carbon-oxygen bond length is a little bit smaller. We would expect it to be a little bit smaller because the oxygen is more electronegative. So it's going to pull in the electrons a little bit tighter, and therefore the bond length gets shorter. So that makes sense to us what the structure is relative to that of what we've already seen before. I can also compare amines, and when I look at amines, we have alcohols in which you have this kind of bent geometry. Amines have three substituents coming off of the nitrogen, and the nitrogen's also sp3 hybridized, which makes the geometry around the nitrogen trigonal pyramidal, right? Because it would take on an electronic shape of a tetrahedral, but the pair of electrons on there we don't see, and therefore the shape of an amine is trigonal pyramidal. And I can certainly compare the carbon-nitrogen bond length just like I compared a carbon-oxygen bond length to that of a carbon-carbon bond, and we see that it basically fits right in between that of a carbon-carbon bond and a carbon-oxygen bond. And we could predict that this was the case simply because as you increase electronegativity of the atom, you pull the electrons closer, and so the bond length decreases. So here I have ethane. I already showed you the bond length of that carbon-carbon bond being 1.4 angstroms. If I compare that to methylamine, the bond length of the carbon-nitrogen bond is 1.47 angstroms, and of course I already talked about methanol being 1.43 angstroms, right? So you see as we move toward a more electronegative element, the bond length decreases. Now, one of the cool features about amines is they undergo what's called an umbrella flip equilibrium with an sp2 hybridized nitrogen in the transition state. What do I mean by this? Well, let's think about stereochemistry for a moment. And if I have an amine where the three substituents coming off of it are different. So here's a nitrogen. It has an ethyl group, a methyl group, and a hydrogen. And then, of course, it has its pair of electrons in an sp3 hybridized orbital. So this is where I get that trigonal pyramidal shape to it. Now, interestingly enough, that nitrogen is a stereogenic center. It's a stereogenic nitrogen because it has, in essence, four different things attached to it. It has an ethyl, a hydrogen, a methyl, and a lone pair of electrons. The lone pair of electrons are a group attached to it. I could assign this an absolute configuration if I wanted to, and certainly if I want to, of course I want to. The electrons are the lowest priority, right, instead of a hydrogen, and therefore this would be take on an R absolute configuration. So the way that I'm going to name this is R N-methyl 1-ethane amine. Now I could name this in a couple of ways. I could name this R-ethyl methyl amine, or I could. I'm just simply showing you a little difference. So I can name this ethylamine, and then a methyl group coming off of the nitrogen. So that's where that capital N comes from. The methyl is coming off of the nitrogen. So N-methyl, and then 1-ethane amine. But this has stereochemistry to it. So do we have to now think about the stereochemistry of all of the amines? Well, not really, and this is why. Because this umbrella flip occurs. And what happens is the nitrogen can go from sp3 to sp2, and if we think about that process that occurs, sp2 atom is trigonal planar, which means that now the lone pair of electrons are in a p orbital. So I have my lone pair of electrons in the p orbital, but I don't, I lose that chirality, right? Because if it's planar, then that means that that it is symmetrical. I can draw a plane right through all of the substituents, and therefore I lose chirality. Now, so this umbrella effect means that the substituents can go from essentially one side to the other side. So now my ethyl group can go up, my methyl group can go up, and my hydrogen can be pushed up, and now I have an sp3 hybridized nitrogen with a lone pair of electrons that are going in the opposite direction. And notice if I think about the absolute configuration of now this stereogenic nitrogen, I see that it's S. So I go from R N-methyl 1-ethaneamine to S N-methyl 1-ethaneamine. What does this mean? Well, this is happening in equilibrium, and it's happening very quickly. And therefore, it implies that amines, by virtue of this umbrella flip, are not chiral, but they exist as rapidly interconverting enantiomers. And one of the reasons why they're not chiral is because they go through this achiral transition state where the nitrogen is briefly sp2 hybridized. So any chirality that it may have actually it loses as it goes through that umbrella flip. This is for, now notice I say this is for almost all amines. There are some examples where nitrogen is in very small rings like aziridines where this umbrella flipping does not occur, but in almost all other cases it certainly can occur. Whenever there's any flexibility in a ring, then this umbrella flip occurs and you lose chirality. And the last substituted alkane I would like to talk again briefly about is ethers. And the reason why I say briefly is because, well, in essence, ethers are very similar in structure to alcohols. Alcohols, remember, are organic derivatives of water. Here I have methanol. That bond angle is 109 degrees. What's the difference between an ether and an alcohol? You're removing the last hydrogen and replacing it with another alkyl group. So here I have dimethylamine, and if I think about the bond angle, of course, I should be able to predict by now that that bond angle is going to be larger than that of alcohols, simply because now I have two methyl groups, both of them are taking up more space, and indeed I get 112 degrees. Now, one of the things that I want you to think about is the hybridization of the oxygen. We typically say that that oxygen is sp3 hybridized. As it deviates from 109.5, it starts to take on a little bit of sp2 hybridization. Not a lot, but a little bit. And so it's still, maintaining most of its sp3 hybridization. We say it's nearly sp3 hybridized. Just like that of alkyl halides and alcohols, when you start to deviate from that bond angle, then you're introducing a little bit of different hybridization. All right, so that's kind of gives you a general sense of the structure of these alkane derivatives, these substituted alkanes, and hopefully it kind of all makes sense to you how we're progressing from one to the next.